Good morning once again, and welcome to our training for today. Once again, let me start by showing the progress of the training. Initially, this training was initiated by the Nigerian Space Research Development Agency in collaboration with the Africa, and it should be a series of uh, 5 workshops, five sessions, you can say. The first one was the intro to the Africa platforms. The second talked about the agriculture and food security. The fourth one will be today, talking about water resource management and flood risk mapping in general. And tomorrow we talk about urbanization and coastal erosion. While on a Friday, we work together, see how we can develop a use case, and we call everyone to be able to think about use case depending upon his or her area of interest. And of course, for this, I'm always choose to simulate and I prepare this presentation with Kenneth Mobeya, who is our capacity development lead. And today we'll be talking about the applications on water resources monitoring, especially with the focus on the water extent and flood mapping. So I want to take much time on the Africa, the solution. As I said last time, we were born from Jerusalem, Australia, and we are there to provide free access to EWA data through an open data cube infrastructure. And also we try to empower governments to use Earth observation and geospatial technology in general to inform civil initiatives that aims to adapt and mitigate climate change impacts, and also ensure food security and they comply with SDGs in general. So the process is very simple. We collaborate with partners across the continent, especially partners. We have offices in Nigeria and others in the region, national space agencies, and other partners with the continent. We identify the users or the users' needs. We try to co-develop uh, some services, but also we host data in associated formats for people to access them in an open data technology. And then everything is free. You can use whatever interface depending upon your familiarity with those particular technologies. And of course, I put in place a learning platform to make sure that people could improve their skills in EWA data processing and analysis in general. So several tools were developed in terms of notebooks, Jupyter Lab, Jupyter notebooks that could be people to run the lecture, or even they can customize them and be able to work with the phenomena as you've seen previously. So among the products we have in our database, we have discussed about crop extent fractional cover, just when we were talking about getting food security. But today we'll be mostly focusing on water observation from space, geomads and water body services that help us to monitor water extents and its flood impact. So interfaces, I want to go back to them because I had Team Map, which is very user-friendly, interactive web mapping, and you have the robust cloud computing interface, which is the sandbox. And of course, you can use the classical softwares and connect with the Africa database and enjoy the free datasets. And lastly, please feel free to have a look at our learning platform just to increase your knowledge. We have almost 11 courses that are free accessible. Now, when you go to the sandbox, which is very key, a robust computing interface, we have a lot of notebooks that could us to understand water in all aspects, from water extent, but also to water quality, especially focusing on turbidity and profile content, but also monitoring wetlands using both radar and optical sensors. And also we can do some robust modeling on water discharge. And for discharge, we can forecast water extent, but also we can have uh, shape files of water bodies across the continents. So if you go into our sandbox, we have several notebooks that were developed, but today we focus mostly on this wetland monitoring, um, also the monitoring of water extent using the water observations from space service. That is the continental, uh, trying to understand the annual summary, but also we can use it to understand the seasonality. The profile content, just to understand the level of profile A in water as a proxy of eutrophication. And also can monitor water quality, try to understand the sedimentation in water. And for each notebook, all the processes were well documented, their location, and even input data, and also the contribution to each SDG. For example, this product called WOFS, it translates observations from space into is to consume information in the presence of water, even the occurrence of water. And it helps countries, of course, we use the service across the continent to map, visualize, and put in place better management framework for the water resources, depending upon their trends over time. Also, we have the other one we call water body. It's a continental service that was processed through which we mapped around 700,000 water bodies, and these ones are available in a polygon format, and then they could help users to view and analyze time series of surface water for individual water features, understand changes in water bodies over the past 3 decades until today, and also they can help us to understand the impact of extreme events and plan for appropriate actions. I show you the water bodies. Yeah. But how does the water body service look like? Please ignore the title. You don't see Bele. It is an area, Olukachi Galiko in Nigeria. Sorry for this mistake. And for this water body service, as I said, you can download shell files and you also have all specifications here, but I can use the geographical maps to show you how it works. And for our study area, I was displaying. I can share this in the chat just for you, for each of you to have a look at the example I will be uh, showing. So once again, I was working on this area in Nigeria, but while I'm waiting for it, when you go to the Africa platforms, uh, you have the option to go through the Africa Continental Services, and you can go to surface water bodies, then you can add them, and all water bodies at continental level are displayed in a shelf file format, and they will take longer depending upon the data connectivity. And when you zoom to Nigeria, of the display quickly, they're taking longer to display. While waiting for it, let's have a look at this example. Maybe this one was displayed already. So I was working on this water body, and we can remove all and go and add our water observation from space. Hopefully they display quickly, right? For this water body, when you click, when you click, let me go to full screen. When you click inside this water body, for example, it is you can show the raw data of the characteristics of the water body, the identity, the identifier of each water body, unique identifier, like this one, the parameter, the last observation date, and everything related to this water body, and the area in square meter, and so on. And also, on a single click, we can expand the analysis and have this nice graph that shows the weight area in square meter. If you can see, that's the trend of this water body over time. And of course, this curve could be monitored to see how this water body has been increasing in extent from 2024, and the fluctuation over years until nowadays. You can even zoom in with the exact date. You can also zoom out to just a kind of a compressed uh, format. And from this, what we can do, we can even download the raw data, and it could be shown in a CSV format. So this is an example of how we can deal with the Africa water body, and you can also have information about data. And when we go to the information about data. We go to about data. About data, it could provide us it shows the API for this water body, but for water bodies in general, we have all the description here, specifications which are available, and just on a simple click, I can share with you all specifications, limitations, and the potentials of this water body service for you just to have a look and enjoy. But also, the most important stuff also here is that you can have an option to download here to download this service in shape files and maybe work from your PC. And I've shared the link for if any of you would like to download this service. This was one way of using the Africa maps to understand the extent of a given water body, but also there is another product service called water observation from space, where we can map water bodies across the continents. You can see all water bodies are there over time, and we can try to find several areas, any given area, to see if it was flooded or not. Let's take, for example, this region for this Niger River. There you can, whereby you can see, we can check the frequency, but also we can see, try to see where there is permanent, even temporary water over time. And that's why I went if you go back to the presentation, I went to, this was the case of showcasing, but also I went to Lokoja River, and I tried to compare 2015 to 2020, and you see how 22, you see how 2022 was flooded in that area, and that was the reason why I see some of the local TVs and magazines report this incident in 2022. Um, Floods on the Okoja River affecting both crops and settlements in the area. And that's why, in a collaboration with the Afrigists, we did a short research, short work on this. And so, to map the water extent, we can do it across Africa. For example, for Lake Chad in your region, that's where you can see where we have what is appearance, so kind of lake shrinking, but also you can see flow between 2018 and 2021. The lake extent was good compared to the previous year. The same for Lake Tanganyika, we can do detection, Balingo, and other water bodies across the continent. Also, other applications, like Ngani in Botswana. Also, we were able to track the water extent over time, and then this inspired and integrated watershed management projects in the area. We thank the University of Botswana, especially Professor Bogire, for the support. But for water resource monitoring, there are two aspects. The first aspect should be understanding water bodies, the trend of water by seasonality. And this is very key because it helps people to plan for intervention in case of floods or any other natural disaster. Uh, and also, we can understand long-term water uh, trends. This is where we use our service called the water monitoring from space. We can understand the annual trends of water, and you know that each season, if we're able to understand the trend in water, we can plan for irrigation, can plan for disaster risk control. That's where we should go into our sandbox and see how we can understand water seasonality, and also we can understand the water in terms of not only seasonality, but in terms of uh, uh, evolution dynamics over time. For example, in the sandbox, using Sentinel-2 images, we're able to derive uh, the modified normal difference water index that will us to understand the time series This started from 2016 until 2024. And each year we divide it into 4 seasons. The one starting from 1st December to the end of February. The second one starting from the 1st March to the end of May. The third starting from 1st of June to the end of August, and the last one starting from 1st September to the end of November. And if we see in our region, you can see that from 2017, 2016, and onwards, you can see that the two last seasons are characterized by water extent. But once again, as you see, 2002 has a larger water extent compared to other years. And this this you can see even on the graph, this should go or due maybe to higher rainfall. And that was an alarming situation in the region. But once again, how can we run this analysis in the sandbox? I can call everyone to uh, try to open the sandbox, because here I was trying to show you the water observations from space for this region. While people are still opening the sandbox, that you could go together, it can display this water observation from space, which not that quick because of the connectivity. And then you can see how around the river we had a lot of floods, and how these floods you can compare years. You can do a comparison, maybe compare uh, maybe 2000 as a baseline, and keep maybe 2024 as our year of comparison. This was 2000, and you see how this area has been affected by floods over time, and it's incredible. And imagine the losses that these floods should have caused uh, around this year. I can share it with you in the chat, just for people to enjoy or try to explore this phenomenon the way myself am exploring it. So once again, um, I think everyone is inside the sandbox, and we can go together. When you go into the sandbox, uh, you go especially into the folder known as uh, your example. But once again, if you open the sandbox, you have a landing page where you can go and explore some themes. Among the themes, we have what you call um, surface water, and all these notebooks you can see were developed just to contribute to the uh, mapping of both um, uh, of surface water in terms of both extent and quality. And please feel free to have a look at them. So if you go in the folder called the old examples, inside there are a lot of notebooks. But for me, I would advise that you work on 3 notebooks for today. The first one should be called um, uh, water monitoring using water extent using WOFs. WOFs being water observations from space. This is the Africa Service for Long-Term Water Monitoring. The second one will be the second one will be uh, water extent using Sentinel 2. This one is a seasonal water analysis. And the third one should be what you call radar water uh, uh, detection. This one, that's about use radar data just to detect water. So what it suggests is that you right click on each one, you duplicate it so that you can work in the duplicate version. Once again, Sandbox is a working environment, not a permanent storage of your data and notebooks. Make sure after each session, you keep a backup of your version because whenever you log out, uh, all changes will be automatically erased. That's to manage the special interface. Either you connect your notebook, you connect your sandbox to your Google Drive or to your GitHub repository, or you can even download the notebook and keep it in a safe environment. And when you go to our social media, especially on our YouTube channel, there's a video on how you can easily back up your work. Then we duplicate this notebook. Then we gave it a name. Mine, I gave it a name. I said Wolves Nigeria. Was this today about Nigeria? Because I have a lot of notebooks. So I said this is Wolves Nigeria for me. And for this notebook, what I did, it is well detailed. It has a title. I hope most of your artists were able to open the notebook because I want to share the coordinates and buffer zone for the area on which we are going to work. Please confirm if you're able to access your sandbox and able to open the notebook on water extent using WAFs. Please put your thumb up. I think to make sure that I'm not alone. I'm not talking to myself. All right, thank you, Erika. And also, uh, I hope most of the team members also are able to access access the sandbox. Samuel, you raised your hand. Any comment or any question? I,
Good morning. I can't access the sandbox.
uh, uh,
I can't access it.
oh, actually, okay, 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 great. Oh, thank you. Sorry for the incident. So, um, actually, when you open this notebook, what you see first of all a description as usual, the title, and also you see the data to be used, and also some keywords, even the context that's on the four aspects of the SDG indicator 6.6.1, dealing with the water ecosystem, and this we do only able to kind of monitor the spatial extent, while through our notebook, we're able to attain the quality, the quantity, even the health or state of these ecosystems. And we'll be trying to understand the long-term water extent. And first of all, we load the packages as we did, and the application will be the water uh, extent. And we'll be able to also specify our study area using the latitude, longitude, and also the buffer zone. And and what I did, I can share this line for column 3. What you do once you put it, you start your kernel and be able to uh, run all cells one by one, and also the time scale uh, starts from it starts uh, from 1990s to 2024. Also, I've shared in the chat for people to go together with myself. And when display the range, we have this is the Lokoja uh, uh, Lokoja region, and then in this Lokoja region, that's whereby we are to run analysis. First of all, we wrote our data sets, transferred the time series, almost 29 20 time series from 1990 to 2024. And we should clip our data to the size of our study area, and then we can display some time series. And as I said, you can see that 20, uh, 20, uh, 2022 was more flooded compared to other years. And you can also produce some animated and good animations, and that's on which you can see how how the dynamics of water extend in our study area. And of course, we can also be able to convert our pixels into a unit surface unity, and then use a threshold of 0.2 to differentiate aquatic and aquatic runs. And I know that everything below 0.2 in terms of uh, modified normal difference water index is not water, and anything beyond 0.2 is classified as water. And you can produce this graph, and you can see that 2022 was the most flooded year in our area. You can also determine the maximum and the minimum of, you can see that's 1998 and 2022. Uh, there, there is a very big difference, but also I was questioning once again if 1998 the river was not there, or maybe it's the poor data quality. Also, that's something you should cross check, try to question, because in each analysis, you should always be cautious in interpreting the outputs. And also, you can compare two periods you want. I've compared 2019 and 2024, and you can see, although we had floods in 2000 and uh, and 22, but it seems that after the life became normal, and the flood areas were good, or were um, not longer flooded in 2023. And also, if when you compare 2019 to 2024, you can see the balance of the area would be approximately 1.5 square kilometer, which is not very big. And but if we compare to 2022, the area was that huge. And this is a good way to understand the long-term water dynamics, combining both spatial mapping, even statistical analysis. And some will ask, now we have the flooded areas, but can you identify key infrastructure and maybe corporate that will be affected. This is what we did with our partners that are affiliates, and I showcase this um, in the presentation. Once again, we can understand the seasonal water extent, but this time we'll be using the water extent Sentinel-2 notebook in the notes examples. And please, once again, you can duplicate it, rename it however you want, and you should make sure that before you log out, you save your work, and also maybe keep your notebook in a safe environment as a backup. So the if you use the same the notebook using Sentinel-2, the processes are the same, but Sentinel-2 could able to depict the seasonality within our analysis, and we'll be using the MNDWI index as a proxy for water mapping. We load our packages, use the same application, and until we get, I should I just started I should run the notebook because I had started the kernel. It may take a few minutes, but while we are be okay on the same area, and of course they will be loading a lot of Sentinel images, and this could take longer. But meanwhile, let's go back to the presentation. What it will give us? It will give us the same results I have interpreted, and also the animation will be showing the seasonality and try to give information, and also can have a graph over years. For the WOFS data, always it's annual summary comparing year by year, and you can monitor the long-term time series. And of course, giving us the same results, 2022 being the most flooded year. But also we can use a reader dataset, kind of with another notebook known as reader data water detection, and through which we can classify water extent. You can have some first color images from reader data, but also we can understand the level of precision in terms of standard deviation. And this notebook also is available, and of course you should be able to interpret the leader datasets, which are not as optical ones. So if we go back to the notebooks we were running, you can see that we have the term series. We have 557 Sentinel-2 images for the study area. We can now clip them, and now at the level of producing the water index, and imagine trying to do aggregation of all these images will take longer than we can imagine, but we can jump to the radar Sentinel-2 radar data water detection, and of course due to internet I have to run it once again and wait for the analysis. But let's go back to the Sentinel also, which is still processing. Then if we go back to the presentation, what I said in collaboration with the African Regional Center, we were able to combine uh, the land use map uh, and the distribution model and try to classify the level of vulnerability to floods uh, for each area, and you're able to uh, uh, high flood prone built-up areas. That's why in the light red, and we had high flood prone croplands in yellow, medium flood prone built-up areas. That should be in purple, the same medium flood prone cropland in green, in light green, and also some areas should be classified as affected. And this is very key because it could help people to take a decision based on the, the classification we provided. And if we're about to build some houses to develop the city, we should try to expand it towards the unaffected um, uh, areas. And we can also try to compare the or to combine the water extent using both Sentinel data and WRFs. And you can see if the rainfall is increasing, according to WRF's product, the water body was increasing on an annual basis. The same applies when you use a radar dataset. And now, let's say that radar dataset is better because it can penetrate crowds, and it will be a good solution for analysis in tropical Africa. Also, the other thing we did, we can uh, uh, try to understand the dynamics of water using the Africa Wetlands Insight tool, which is able to understand the dynamics of water uh, over time, but also the aquatic vegetation around water, it is stable or changing, wet areas, even dry area. The idea is that we should always keep our water extent stable, even the wetlands, even the green vegetation. If the dry vegetation in the bare soil is invading the green vegetation, wetlands, and water, then it's dangerous because our water body is shrinking over time. But also, we can understand uh, the quality of water. Here, we can use several proxies. We can either use the normalized difference profile index just to understand the concentration of chlorophyll A in water, and we can understand this over time, but also can understand the relationship between the extent of water body and the profile concentration over time. And you can even see on our water body visually, you can see the content, coffee content was uh, higher in 2021 compared to 20 in December compared to February 2021. This is also feasible, and of course, we can do some long-term animations on water bodies, and the notebooks were shared. And then this is our Bokolori dam, and we try to understand it from our water bodies. It has identity. This is the ID, and we can always run the animation that shows how our water body has evolved over time. And this starts from 2014 and onwards. And of course, we use this our WRF's data yet to mask out other non-aquatic areas around our water body. And so kind of combining video maps and related statistics just on a single click. But also we can do some seasonal animations and which put together mostly the geomads and also wolves to mask out all aquatic areas and also the water bodies, the shell files, but also then for data shapes which are global running for data sets. And as you can see how our water dam has been evolving, also how the precipitation has been increasing over time. Just after each rainy season, the water uh, the water extent is increasing per each time, and then we can even export statistics behind all those analysis and produce a good time series in terms of the impact of climate dynamics on each water body in any region. And also, we can understand the turbidity for lakes. This was the example of Lake Gis in Senegal, Turkana in Kenya, but also I tried for Bokolori Dam and the other areas in Nigeria as well. We can also understand the profile content as it showed using both map and uh, and sandbox, and they can compare any water body over time. And if we go back to the sandbox, just to conclude, we are trying to understand the seasonality using segment two data sets. What I presented in the PPT was produced from here. You can see that we can produce some nice time series over time, trying to show how our water body evolved over time. Then message here will show the start of each season, and note that here are four seasons, and that the last two seasons, that's the second one from 1st July to end of August, the fourth one, that's the third one from 1st July to end of August, the fourth one, that's from 1st September to the end of November, were created by a higher water extent. I think also the rainfall is a higher there too. So we can get the curve and also can compare any year we choose. And see if you compare, for example, 2016 and 2022, and see how our study area, that local area was flooded. And also we can compare any years we choose and also come up with a change detection map. For example, you can see that here, comparing 2017 and 2024, you can see that there is no water to water. There are almost to 10. If you do the difference, you could see that we have almost 10 square kilometer that were somehow uh, flooded. Also, talking about the red water, I wrote so where you can try to use the same. This is called free data, and we can go through it. We can uh, work on the same area, specify the area of study, as you can see, and the same area of study. Then you can try to produce the vertical polarization, plot it, and also you can plot the horizontal polarization and try uh, to combine all the polarizations and also convert um, into digital number, and also uh, we can plot RGB time steps showing how the river evolved over time, and then we can come out with uh, a lot of techniques just to define thresholds to classify aquatic and aquatic areas, and then come out with the strategy areas. Those are pixels that could be later on converted into a area in square kilometer, in metric unity. Then we can also assess uh, the accuracy of our classification by using the standard deviation. And you can see that standard deviation is almost always less than 5%, which is a good result to apply the data. The same notebook is always found under the folder load examples, and you can say let the auto detection. You can run the notebook, and of course use the coordinates I gave you, and you choose any time scale you want. The last part also, this is the wetland insight tool. I told you it's also here inside our notebook. We asked the sandbox load examples. We can what that it does. Here it is a workflow, and when the flow is very simple, what it does, it is you inputting data, it is taking each pixel, if it's a cloudy or no data, so we leave it out. If if it is clear, we just classify as water, off as water. We have open water. Then we can try to classify wetness, and then it's wet. You can also classify land cover as gravitation, and bare soil. So we can run the kernel immediately through this notebook, and our application was already loaded. It should be up to us to define the area on which we're going to work and the date. That quick because of uh, my internet connectivity. But the idea of that we can draw a polygon around any water body and come out with okay, now it's okay. Now it works. We can go to Nigeria. We can choose any small water body just to be uh, quick. So let's choose this one. Now the catch here, if I can say, this was is called Gorora Dam Reservoir. We can choose the date. Let's say let's take maybe 20, 20, 2024, January 1st January, and also compare to let's say the same year, let's say 31st December, and the sampling frequency it take 3 months, and we be exporting CSV and the example uploads for our outer body. And next step will be we have to draw a polygon around our outer body manually, and they should try to improve the precision. But what I'm going to do, I will do it quickly, just for the sake of time. Okay, then we just check if the polygon area is a little bit is 91 square kilometer. Then we can run our analysis, and it is loading data sets. It is calculating the wetness, trying to understand vegetation cover, and it will provide a table, CSV table, with the water coverage, water percentage of water coverage, and looking vegetation, dry vegetation, and bare soil. And in addition, it will give us this graph I've been sharing in the PPT. And the last part of this presentation will be to understand the profile content in water bodies. And I try to run this notebook uh, for it's analyzing profile A content in water, and it is well defined which are the differences, and the normal difference profile index was used to do this calculation. And once again, I have to run it, and also the notebooks on water animations and the others are always under the old examples folder. Please feel free to have a look at them. So just to conclude, we have structured this in several courses. Like this is just one, try to deal with the water resource monitoring, combining both atmospheric aspects, soil moisture, and also other aspects of the water cycle, and just to um, support agricultural practices across the continent. Please have a look at the course if we are available on our our learning platform. And of course, we have several courses, including the one on water resource monitoring, a lot of tutorials related to water and flood risk mapping. You can check on our social media. And most importantly, we have a course on water resources that was recently updated. You can do it and have more skills on the use of the Africa platforms for water resource monitoring. And of course, we thank you for joining us for our weekly sessions where we discuss different in your dataset analysis. And of course, uh, I mean there thank partners and can just email, but I'm not closing the session, but I am just giving you time for you. Uh, when you are stuck, you let me know. We can work together, at least on one notebook, and try to get the results. But if you have produced your own results, please feel free to share your screen and show to the group the work you were able to do. And I open the floor for discussion, exchange, uh, challenges, opportunities. Over to you. Thank you. Anyone in the room with comments? Question would be or I say who wants to share the results or the analysis he or she has been doing while doing the demo, or was anyone able to run any analysis? Please the floor is yours and the discussion is open. Thank you. No comments? No one from Nigeria space? Just to open the floor to the whole team. Can you hear me at least?